Right, in 2007, great year for the Leaving Cert, higher level chemistry, question 10b. Yeah, something here to do with the equation of state of an ideal gas and the gas laws. Now the first one's simply a definition. You learn that off. Equal volumes of gases under the same conditions of temperature and pressure contain equal number of molecules or equal number of moles. You can see why I said moles as well as molecules for a part coming up here. The second one, now once I see a lot of information like this, when I see pressure, temperature, generally maybe a volume or something like that, straight away I'm thinking the equation of state of an ideal gas. The same equation that you use to determine the relative molecular mass of a volatile, a low boiling point liquid. In that sense, if it's of an unknown liquid or an unknown gas or liquid, here we know what the gas is. It's CO2. So I'm going to write out the equation of state of an ideal gas, PV equals nRT. Now they've asked me what volume. Now P stands for pressure here, measured in pascals. V stands for volume. Now the funny thing here is the volume's measured in meters cubed. The reason it's meters cubed is to do with your pressure. Pressure from junior cert science is force per unit area. Force measured in newtons, area meters squared. So we need to keep the units consistent by having meters. And the number of moles, our universal gas constant, that will be in your front of your exam paper, it's generally 8.3 or 8.31. And T is the temperature measured in Kelvin. These gas laws have to be in Kelvin temperature. If you think of Charles' law, directly proportional to the Kelvin temperature. So first thing, when they say what volume, I'm just going to manipulate this formula to get V on its own. So it's nRT over P. Now we have R, we have T, we have P. We just need to work out N, which is the number of moles. Now, since we know the gas, we know there's 2 kilograms. Now, if we're thinking of our mass or mole triangle, it's mass and grams up at the top, not kilograms, mass and grams. And to go back to moles, you divide by the relative molecular mass. So the relative molecular mass of carbon dioxide, we'll work it out. 1 carbon, 2 oxygens. 44. We change this here to grams. Kilo means 1,000, kilometer, kilogram, 2,000 grams. So the number of moles is the mass in grams divided by the relative molecular mass. Not going to work out to be a nice natural number. 500 over 11 or 45.45. Now all I'm going to do is horse in these values into this equation here. I'm actually going to use, what did they say, what volume? Yeah, I'm just going to use 500 over 11. So number of moles, 500 over 11. R, as I say, I don't have the exam papers with me. 8.3 or 8.31, not make a massive difference. It'll say in the front page of it. T, temperature in Kelvin, it's in Kelvin, we're good to go. Don't need to add on 273. And then your pressure in pascals. You can change that to 101,000 if you wish. But the less you do, nearly the better here. So 500 over 11. And there's by 10 to the power of, same as what you use in the mole. And I'm getting 1.08. Say 1.085. And this is in meters cubed, all going back to your pressure being in newtons per meter squared. Now there's a second part to that part 2, and it says what mass of helium would occupy the same volume at the same temperature and pressure. Now looking what we said here, equal volumes of gases under the same conditions of temperature and pressure contain equal number of molecules or equal number of moles. So equal volumes of gases, let's call it part B, under the same conditions of temperature and pressure contain equal number of moles. Now from up here we learned that there were 500 over 11 or 45.45 moles. So helium is a gas, it's a noble gas, group 2, full outer shell, very stable. So it's going to have 45.45 moles or 500 over 11 moles. And then just to work out the mass of it, we've got the number of moles multiplied by the relative molecular mass. And we have it. I'll show you another way you could do there. More than likely the way I would probably do if I was in an exam. So I get 181.81 grams. 181.8 or 82 grams. And I don't know, maybe I'd ask you to give it to the nearest whole number, I'm not too sure. You could have, if you liked here, worked out n using your equation of state of an ideal gas. I'll not do it. I'll get it teed up. So there's my number of moles, my PV over RT. I fill in for my pressure, 101 point, or 1.01 by 10 to the 5. My volume, which I've worked out to be this. My R, 8.3 or 8.31. And my temperature, same temperature and pressure, 290. Now I'll probably not get 500 over 11, but I'll get in and around 45.45, 44, 45. I'll get a slight deviation, but it won't be massive. And then the last one, why is CO2 more easily liquefied? CO2 is more easily liquefied. Here we're looking at anything to do with solubility or boiling points. You're chatting about the intermolecular forces. So just compare them. CO2, polar or non-polar, it's a polar molecule because of the electronegativity difference. It's a relatively large molecule, it's a relative molecular mass of 44, while helium, a very small molecule, relative molecular mass of 4. So CO2, I'll just skim down things. Polar, larger molecule, therefore stronger intermolecular forces. It has what's known as dipole-dipole forces. Helium, on the other hand, is non-polar. It doesn't form any bonds between any other compound. It's a small molecule, smaller number of electrons, very weak intermolecular forces. And intermolecular forces that you're dealing with there, getting out a shot here, is van der Waals. You're my van der Waals. And that's it.